Hello everyone, welcome to my talk. My name is Chen Yuan, and I'm a PhD candidate from Arizona State University. Today my topic is lithium isotope variations in humite from Palabora in South Africa. First, I want to thank GSA and the session committee Justin and Daniel for giving me this chance to show this work. Also, I want to thank Linda, Tim, and Axel for their help with the experiment. Today we come here for a reason, to honor Dr. James D. Webster. He is an ASU alumnus who passed away last year. I have never met him, but his devoted research in magmatic geochemistry and experimental petrology will always inspire me and the younger generation who are interested in igneous systems. Why humite and why lithium isotope? First, we need to know what's humite. You probably know that olivine is the most abundant mineral in Earth's mantle. If you put olivine with water and put them in the upper mantle condition, then you will create humite group. Depending on this N number here, there can be 4 different subgroups. Also, we found lithium element has a similar ionic radius compared to magnesium, so it can substitute for magnesium in Mg-rich minerals, such as humite. So humite might be a very good candidate to study lithium isotope. Our motivation for this study is to test whether lithium isotope in humite work, and if it's able to trace complex cross-mantle recycling process. Here is our sample. The left is the optical image. The green and yellow mineral here are humite. We enlarge this area so we can see what does humite looks like in cross-polarized image. As we can see, this humite, it looks very similar to olivine, but it's not olivine because it has a few weight percent fluorine. The first thing we did is to go to the electron microprobe. In the BSE image, we see there are 2 different phases of humite, light phase and dark phase. The EMPA data tell us the dark phase has more fluorine and magnesium compared to the light phase. Using the EMPA data, we calculate the N number here. The light phase is 3 and it's called humite. Dark phase, the N number here is 2 and it's called chondrodite. Both of these are the 2 of the 4 subgroups of humite group. We also found that the darker phase possibly formed later than the lighter phase. As we can see, most of the dark phase distributed at the boundary of the light phase, possibly formed by the reaction of light phase with the late carbonatite melt, represented by this vein. If you have no idea what is metasomatism process, it's the chemical alteration of a rock by external fluids or melts. In addition to the rim dark phase, we also found a few large individual dark phase. There are almost no obvious light phase humite here. With these observations, we go to the same measurement for lithium isotope. The delta lithium 7 is calculated by this formula. Basically, we are comparing the lithium 7 and 6 ratio of our sample to a standard. If you have more positive delta lithium 7, it means you are enriched in lithium 7. Otherwise, you enrich in lithium 6 compared to the standard. Here is the result. The red is a light phase, and the blue represents the dark phase. We can see although there is a large variations, but we cannot tell which phase is more positive which phase is more negative, because the results are very similar and they are mixed. So how did it happen? Then we go to the scene section again. We found there are complex structures. For example, in the interiors of the light phase, we found there are some small patches of dark phase. Also in the dark phase, we observe there are some relative light phase there. As you can imagine, during the experiment, it's also possible when you are measuring a surface for one phase, but when you're going deeper, it will change to another phase. This is possibly seen by this same depth profile. As we can see, the surface is very positive, delta lithium-7, but the deeper part is more negative. So we realized we need more high spatial resolution measurements, and also it's better to measure a very shallow part of the sample to avoid the mixing. Here is the nanosim result. Here, generally speaking, we can see the lighter phase is more positive in delta lithium-7 than the dark phase here. But it's clear there are still some variations and the mixing point between them. So what's a possible reason? Another advantage of using nanosims is we can measure more isotopes during the experiment. After realizing fluorine is important, we also measure fluorine during the nanosim experiment. In this figure, we can see, although there are still two major groups, light phase, dark phase, but there may be more subgroups within the light phase and within the dark phase. For example, this two dark phase has less fluorine compared to this dark phase. And also this two light phase is more rich in fluorine. And also it has a different delta lithium-7. After checking with this group, we found most of these measurements are from individual large dark phase. That's possibly from carbonatite melt. We can see it's very rich in fluorine. So you would probably agree, if the light phase had the least fluorine, it may suggest it has least influence by the late carbonatite melt. So we think this group are the earliest humite, that they have very positive delta lithium-7. Of course, there are some mixing points between them. These 5 points, we think it's mixing during the metasm process. Now let's focus on these 5 points. In the left figure, the x-axis is the inverse of lithium contents. The y-axis is still the same, delta lithium-7. As we can see, if you increase the lithium concentration, you will have more positive delta lithium-7. What does it suggest? In the right, we give our preferred explanation. The earliest light humite has more lithium concentration than the individual dark phase. This dark phase is from late carbonatite melt. When the melt have chemical reactions with the earlier light phase, the lithium will diffuse into the melt region. Because of this relationship, it suggests lithium-7 prefer to enter melt domain. Otherwise, if its kinetic effect, lithium-6 will move faster, so it will have this relationship, but this is totally opposite. So the result here suggests lithium-7 prefer to enter melt domain during this metasm process. In the end, we give our preferred dynamic model. The earliest humite light phase has a very positive delta lithium-7 and high lithium contents. It's very rare and very different from the normal mantle. but it's very similar to the altered oceanic crust. Also, humite is not a typical mineral in mantle, but it can be easily formed by breakdown of serpentine. So we suggest the earliest humite may form by the breakdown of the serpentine and delivered to the base of a plume by a stagnant slab. With the arising of this plume, it transits another carbonatite melt layer, which has low delta lithium-7. This causes the dark phase and the metamorphism process. We admit there are more possible explanations for the origin of this sample. This is just one of our hypotheses right now. To conclude, we found surprisingly large lithium variations in humite, but hard to interpret. Our results also indicate a dynamic environment during the crystallization of this transgressive carbonatite. Thank you for your attention. Feel free to ask me if any questions or connect me through my email.